My name is Kenneth Dwyer. I'm Applications Manager at NXP. And today I'm just going to talk about getting the most performance out of the LPC4300 family. So earlier on, Gordon introduced an overview of the product. And I'm going to kind of dive into two of the peripherals that are of interest. One of them is the SPI interface, the SPIFI interface. And the other is the inter-processor communication and that protocol and how we implement communication between the dual core of the 4300. So this is what the abstract alluded to, what we're going to talk about. Again, the advantages of SPIFI, SPI Flash, how you talk to quad SPI devices. And we'll explain the inter-processor communication. And we'll see some examples. I have some hardware up here. I hope to get my camera to work, but generally speaking, you'll be able to see most of the Kyle tools running and talking to the board. And obviously, at the end, every participant will get some free development tools, which will make you all happy, hopefully. So NXP, introduction. We're a leader in the ARM Flash MCU area. We've been at this for quite some time. Most of you may know we came from Philips, and now we're a privately held company, or actually, we're no longer privately held. We're on the stock market now. And so basically, we have a clear ARM strategy. So we're focused 100% on ARM microcontrollers. So we have everything from M0, small 8-bit replacement type device, all the way up to the M4 with M3 in the middle. So where does the Cortex-M4 fit into the picture? Well, it's actually at the high end of the system, supporting just microcontroller embedded systems with DSP extensions as well. Cortex-M3 family is a sister product of the 4300 being the LPC4300. And then as you kind of go down the ranks, you get smaller footprint devices, smaller peripheral set, yet still ultimately powerful. They are interesting parts. Today we just announced the 1100 family going into DIP and TSOP28 and TSOP20 type packages. Up to now, we've only released these parts in HVQFN33 and LQFP48 type packages. So that's kind of interesting to note. So the LPC4300, Cortex-M4, everybody's heard about it. All our competitors have a Cortex-M4. So how do we distinguish ourselves from our competition? Well, we try to put some thought into how we implement our peripherals. We make our peripherals smarter. And some of them peripherals I'm going to talk about are the likes of SPIFI. We talked about the smart or state configurable timer, which is a really sophisticated timer. It can be considered a very simple thing, but also can do a lot of complex tasks and allow the processor to do other things like processing, number crunching, stuff like that. So NXP kind of the way we look at the market is that we license the Cortex core, but we add the bells and whistles around the core to make it really a distinguished part, okay? And we'll kind of talk about some of these peripherals as we go through the slides. And my intention today is to talk about the SPIFI and IPC. Gordon earlier mentioned SGPIO. That's a nice block. We'll talk about that on another session. Really interesting is a high-speed USB. We are the only vendor in the market with the PHY integrated onto the chip. So that's a nice feature to have. Also the LCD controller, DMA, motor control centric peripherals, plenty of serial devices like UARTscan, I2C, so on and so forth. And of course GPIOs. So this is a block diagram. So forgive me for the repeat of some of these slides because this is what Gordon had presented earlier, but this is just the introduction. So some of you were here before. I'm just going to breeze through these, and we're going to be going into the demos in a few seconds. On the top left, you have the Cortex-M4 with its NVIC, wake-up interrupt controller, the floating point unit. All our M4 parts have these features, also memory protection. Then on the right-hand side, you can see over here on the right-hand side, we have the Cortex-M0. So now we have two cores in there. Well, what are we doing there? And how do we make them work together? So that's what we have IPC for. That's what we use our inter-processor communication. And then kind of in the middle, you have PLL-centric clock stuff, a lot of analog stuff. We've got ROM with lots of drivers on ROM. We have loads of internal memory, fast single-cycle internal memory. And And we do have parts in the roadmap. We don't have them right now, but we'll have them in Q1 with embedded dual bank up to 1 megabyte of flash. So you have a fully self-contained system that may not require any external memory requirements. You could actually put it all inside the device, which might be nice for sort of security applications. Then on the bottom you have all the different peripherals: USB, Ethernet MAC, LCD controller, quadrilateral encoder used for motor control, RTC, motor control PWMs, and so on and so forth. So this is the story about the 4300. It's flexible. We have unique configurable peripherals. I mentioned them again, SGPIO and the state configurable timer being the most flexible and configurable. The SPIFI is more like an alternative to NOR flash. We'll talk about that in a minute. And then we're the only vendor in this market space with a dual core strategy where you can actually have a really powerful number crunching M4 device core, and also a partner core, a buddy core, the M0, taking care of housekeeping functions, interrupts, servicing things that are not so important, that don't require so much processing power. So that's the concept of this product. Also, just to mention, number 3 is that they are pen compatible with the Cortex-M3 LPC4300 family. So in some scenarios, you may not want the DSP extensions that the Cortex-M4 provides. Why should you pay more for that? Well, we offer you an M3 version of that as well. You still get a lot of the same peripherals. Some of the peripherals may not be there, but if you do not need a number crunching capability, then you could get away with the M3 and save yourself a few cents. Yeah. The performance there actually is one thing to mention as well. The Cortex-M4 and the M0 actually both run concurrently or synchronously at 180 megahertz or up to 180 megahertz. You can PLL that up or down as you feel for your power consumption. You can reduce the PLL to like whatever, 1 megahertz, 2 megahertz, whatever, and save power. The Cortex-M4 and M0, the LPC4300 will go to 180 megahertz. The 1800 family goes to 150 megahertz. Okay, so now I'm going to talk about the SPIFI, this SPI Flash Interface. So essentially, this is what it looks like. You've got a Cortex-M4 or a Cortex-M0 looking out to this SPIFI interface, this SPI Flash Interface. And what does it talk to? Well, it talks to these quad SPI Flash devices. And these quad SPI Flash devices came from the computer area, the computer market, the PC market, where the BIOS was booted by the operating system, and it used to be stored in quad SPI Flash. So they're cheap. There's lots of them around. This is where SDRAM came from, DDR. All the memory, all these memories are all driven by the PC market. And ultimately, they merge into the embedded market when the price comes down and people like to start to use them. So one of the challenges of SPIFI, or quad SPI, and the usage of quad SPI in the past traditionally has been, how do I use this in an embedded system? How do I get the data out of there? How do I execute out of it? It was not possible. We've made it possible by our patent-pending SPIFI interface, right? Serial Peripheral Interface Flash Interface. So we call it SPIFI for short. Or for convenience, SPIFI. So what it makes the quad SPI serial flash look like, it makes it look like a linear block of memory address space to the ARM core. So what you're doing is you can actually see a serial stream of data coming into the ARM core and then being presented in a parallel fashion. So what you have on the diagram there, you have the AHB bus, which is the ARM matrix, the way the ARM communicates to external peripherals. We have our SPIFI with its buffer and its control registers. The SPIFI registers are written to by the boot ROM code in the chip, and basically configures it and allows it to talk to these serial quad or single or dual SPI flash devices. So you can actually either, when it boots up, it comes up in single mode. You can talk to dual mode quad SPI flashes or quad mode SPI flashes. So this is the electrical interface. Again, you have the MCU, and you can see the signals that are used. You have a clock, chip select, and the standard SPI type interface signals, MOSI and MISO. And in addition, then you have the 2 more extra lines. So these make up the quad interface. And again, these are the more detail on what the signals are. They're kind of self-explanatory, but just to kind of cover it, the SPIFI clock will go up to 180 megahertz. It'll go the same speed as the core, okay? But some of the external devices may not support that. We generally use it up to 100 megahertz. Typically, it'll run at 100 megahertz, and it's quite possible when we finish characterization of the part, we could probably go beyond that. The chip select is self-explanatory, and then you have these kind of input-output signals where, generally speaking, for this device, mostly once it's programmed, you're actually using these pens as inputs to the core or inputs to the LPC4300. You're going to be sucking data in out of there. It can also be used for storage, and we allow you to program it as well. But mostly what we see this usage, its usage as a source of data. It's a flash. It's not a RAM. Okay, it's something that it's a non-volatile memory, and generally you just suck things out of there, and infrequently maybe you might write to it. Both operations are possible. Normally it's just feeding data to the LPC4300. So this is what it looks like for the memory map. So the SPIFI data, this quad SPI content, whatever's stored on there, if it's blank, it's all Fs, right? So if it's blank, in that memory space, you will see all Fs. And we actually show 2 memory spaces here. There's a 64 megabyte one in the yellow there, which starts at 14000000 in the address space. And it's 64 megabytes inside, so it goes up to 1800. That 64 megabyte space is actually mirrored in another region in the memory map. So that's great. So I can see the same thing in 2 places. Well, there was a reason for that, and I kind of explain it in the next slide. It's interesting to note that both the lower region on the yellow and the upper region where the 128 megabyte, they overlap. That 64 megabyte reappears at the 128 megabyte space. So what you can actually do is link your program to execute from either or of these 2 areas. And I want to give you the background into why there is 2 areas. So the Cortex architecture has a Harvard-type architecture, okay? So it's got an instruction and a data bus, and then it's got an S bus. So it's got this parallelism where you can have instructions, fetches, and data fetches happening in parallel. And it also has this S bus. So the I and D bus, the instruction and data bus, are used for memory addresses less than 2,000. So if we go back to the screen here, it's the region on the left-hand side. The small region is this instruction data bus space. This is defined by the Cortex architecture. It's defined by ARM. You have to adhere to this to be Cortex-M compliant as such. So as this kind of slide explains, we ran out of space down there, so we had to kind of come up with a way of getting around it. So we did decide to put some of the SPIFI Flash data space in this I&D area. And then we also put it up into the upper area to give us some room for expansion. So as time goes by, and as Mr. Gates here, who's quoted saying that who would ever need more than 64 kilobytes of memory, we have the same kind of concept that, well, we don't want to restrict ourselves to just 64 megabytes. Let's give us some headroom, and we give ourselves 128 megabytes of space. So that means we're future-proofing the device so that if there's larger quad SPI flashes available in the market in the next few years, we have headroom in our system to accommodate them. So I alluded to this earlier. You can boot from SPIFI on this product. So on this LPC4300, you can configure the pens. There's 4 pens. You set them to a particular state. You press the reset button, and lo and behold, the SPIFI will provide the instructions and data to the ARM core, and it'll actually execute out of there. So, okay, so let's talk about the boot flow. You saw the device booting from RAM or from Quad SPI Flash. So how did it do that? Well, it has to know something. The device needs to know something about what's out there. And the way it knows that is that we've worked with all the different Quad SPI vendors, and tested out the hardware and created a boot ROM that works with the quad SPI devices. So every quad device, not every, most quad SPI devices that exist out there will be supported by the boot ROM if they were created in the last 2 years. If something new comes along, our boot ROM will still boot from it. It won't support it directly, but it will allow you to go back to a kind of a safe mode. When your application starts up, then you can switch to full speed mode again. Okay? So this is the idea of the boot ROM. Comes up at 32 megahertz and sends out this standard JDEC read ID command, which is command, can't remember, 93 I think or something. It sends out 93 hex, and whatever is out there, if it's real, if it exists, if it has something in there, if it's a quad SPI flash, it'll send something back. Okay, it'll send its device ID. Then the boot ROM goes, oh, I know who you are, and it'll just pull the chain and or sit down, hit the boot, and crank up the clock and set up whatever it needs to set up for that particular flash device. As I said, if it's unknown, it still will continue, but in a kind of like a safe mode. It's like when your PC locks up, right? It goes into this safe mode. It'll still allow you to read from it. It'll allow you to take your application code to change the clocks to whatever quad SPI is out there, and then you can move forward again. So it's quite a robust little system, and tried and tested. So just want to make sure you understand that the device has a boot ROM that supports many quad flashes. Here's the list of quad flashes that it supports. And this is not just supported. This is actually what's been tested on the hardware. We've tested the hardware with all these vendors, with all these devices. And before we taped out our silicon, we put all this into the boot ROM. So it's hard-coded into the boot ROM. And the advantage of being on the list, I guess, is that your booting will be somewhat faster. You boot up at 32 megahertz, and then you go up to the 100 megahertz really quickly. If you're not on the list, well, you boot up at 18 megahertz, and then that takes, well, 18 minus 32 is whatever that is, 20 or 10, and then, or 12, whatever, 14, right, 14. And then you can crank up later on. So there's a small bit of delay if you're not on the boot ROM list. Just to show you what it looks like, so there's a chip select, S clock, your instruction, and then there's the data. So the boot ROM, the first thing it does is sends out this standard JDEC command. So it's an industry compliant command that everybody in the flash world will adhere to. And this command is 93, I think, or something like that. And the device that's out there will respond with a manufacturer device ID and some other information. I think 192 bytes, up to 192 bytes of information is actually passed back. And the boot ROM will take that information and then decide what to do next. So we talked about it booting. So it's after booting up. And for example, if you did not recognize, if the boot ROM did not recognize a part, you need somehow to get out to the part to decide what to do with it. And we provide this API command or software to allow you to interrogate what's out there. You do initialization, you can do a program, or you can do a erase. The program, actually the erase is actually redundant because by programming it, you can actually erase it. Part of the programming sequence is to erase the area you want to program. So you can consider programming with all F's an erase, right? So you can nearly ignore the erase one, but it's there nonetheless for people that want to use it. So what can happen is you can boot from SPIFI, you can boot from quad SPI flash type devices, start running some application code. Later on, you might want to store some constants out there, some data. We give you an API that allows you to say, take a section of the quad SPI flash that you know your application code is not in, and save that data out there. So it can be it could be like an EEPROM. It's not an EEPROM. It doesn't have EEPROM characteristics in the sense it doesn't have the wear leveling that EEPROMs have, but it does allow you to program it on the fly via the application if that was something that you wanted to do. So how do we call this SPIFI API? Well, there's basically a pointer to a ROM area, which has all the ROM definitions. We provide a header file. We provide you with all the software, and you plug it all into the magic tool, and it'll work. And I actually have a demo of it in a few minutes that kind of shows how that works. So performance, we're talking about performance. That was what we were supposed to be talking about. So I wanted to show you this slide where we talk about NOR Flash. Our part will boot from NOR Flash. We have 32-bit wide interface data, 32-bit wide data bus, so that's 32 pins, and we have A0 to A23 or more of address pins. A hell of a lot of pins to get a bit of data off something. Well, most NOR flashes out there that most people use in the embedded space are 16-bit wide, and you can sort of do the math here and look at the throughput. Well, you can sort of see on the slide here that the throughput for standard 16-bit wide NOR flash kind of goes up to like 22 megabytes per second. And then if you compare that to serial flash, well, obviously a single mode flash that's just got one data line will only run up to 10. But if you go up to dual or quad, you can already see, wow, you're getting performance here. How can I utilize that, right? So that's what SPIFI gives you. It gives you the method to get in there and suck out that data in a quad mode and actually execute from it or use it in an application. So this is why we kind of created this device. Embedded systems are space constrained a lot of the time. Sometimes people want to trade off performance versus the cost of area on a board. Performance can be compensated for by doing things smarter. You can copy stuff from NOR flash and put it in internal memory. There's lots of different ways around that. But if you've got this huge 32-bit or 16-bit wide NOR flash, you're already running into some kind of space constraints. So we're talking about performance, and I mentioned earlier the SPIFI clock will actually run up to 100 megahertz. So what that means is if you've got 4 lanes of data coming back in, that kind of more or less comes to 50 megabytes per second of performance. And of course, how do we measure that? There's lots of different ways. You could just put a scope on it and say it's 50, but then what about the application? How fast does your application code run? That's what you really want to know. And that's application specific. But there is CoreMark, which is kind of like more like an independent benchmark, which kind of benchmarks the performance of execution from this flash and also how efficient the CPU is running. So it does a lot of algorithms, a lot of array math and stuff like that. But ultimately, what this CoreMark benchmark is testing is the efficiency of the CPU, how well it's running out of whatever memory it's running from, be that internal memory, be that NOR flash, or be that SPI. So depending on the device that you have connected out there, it might be a Micron, it might be a WinBond, it might be Spansion. All them guys make quads flash. They all have slight differences, not just the speed they operate at, okay? So the clock is one thing, but their reaction to certain memory reads, certain sequences is slightly different. Some have more overhead, some have less. Some have more depending on the instruction, some have less depending on the instruction. So there's always going to be subtle differences. Every quad flash will not run at the same speed. And then on top of that, well, you have the CoreMark on the left-hand side there. That's the number we want to get. We want to get up to 2, 3, 4, 5, as high up as we can. And then you have the clock frequency of the core. But then there's also the speed of the SPIFI interface. How fast are you running the SPIFI interface? So you can see what happens is as I increase the core frequency, right? The core is looking for more data quicker. Give it to me quicker, quicker, quicker. I want it quicker. I'm really running fast here. And the SPIFI is slowing it down. It's not able to keep up as well. So you can see a drop off on the SPIFI, okay? This is what we expect. If you run at a lower speed, your performance out of SPIFI will be better, but you're not running your core at the optimum speed. The core can do a lot better, right? With NOR flash, you will see something similar. The NOR flash, internal memory at least, internal flash, we have a flash accelerator that has some degree of caching or buffering. And as you start really putting on the pressure onto the flash, that performance will start dropping down. And in this particular case, you can see how it drops. So we're not claiming that this interface will run at top speed at all frequencies. There is a penalty, and we make that known to you, and you kind of have to decide if you can live with that in your application. So this is kind of a comparison to internal memory, right? So if you run CoreMark out of internal memory, okay, so all the CoreMark code is copied from wherever, put into internal memory, and you press the button and say go. The number will be 2, 2.1, 2.2, around that figure, okay? So you can sort of see the difference between the performance from a kind of ideal single cycle memory versus this external quad flash. And I should really have NOR flash data in here. I just didn't get time to get it done in time, but just to be fair and compare, to give you a kind of realistic picture, the SRAM data there, the 2.0 is the ideal case as such for our product. And then the quad SPI data is, well, that's what it is. So you can see that there's a 60-70%, depending on the part, performance difference. So if you run a quad SPI, it's like it's running at 70% of the potential that the part could run at that particular frequency. So some of the concepts that we've kind of talked about for SPIFI has been related to image storage. One of the ideas that we had way back when we started developing the interface was, well, if you're using LCDs, you have a big frame buffer, right? You have a lot of data, and you want to put it somewhere. Normally, with large panels, say sort of like this guy here, for example. Normally, that's actually that is on an SDRAM, right, or somewhere in internal memory. But if you've got a really large panel, you're going to run out of memory fast. You're going to run out of internal memory in these small embedded devices very fast. So what people have done in the past is, put your frame buffer into SDRAM. Well, that's another memory interface you have to load up, you have to configure it, and you have to contend with. So we kind of come up with this idea for some applications. It's actually nice and useful to be able to just point the LCD controller straight out to quad SPI Flash and have your images out there, okay? So you've got a really cheap, couple of pens, 6 pens, right? Device sitting out there with all these images. So as the user presses buttons, for example, these images just get sucked in. You don't need a frame buffer at all. You can bypass the frame buffer. So that's the concept. Another application for SPIFI, we kind of conceived, I don't have a demo for this particular one, but where you have frequently loaded algorithms that you want to run, and you don't want to have them always in memory. Well, you can leave them in a cheap, low cost, low pen counts SPI interface, and suck them in as they're needed. So that's one of the other concepts. That's the solution: low cost and less waste of your internal memory. While the data and the algorithms are stored out there, you can use the internal memory for more useful things. So of course, board space is another cost or performance advantage for the SPIFI interface, talking to Quad-SPI Flash instead of talking to NOR Flash. Our product does support NOR Flash. We're not knocking down NOR Flash. It is useful. It is required. People need it. It's faster. It can perform better than Quad-SPI Flash. But there is a penalty, right? There's cost penalties. And there's also the board space. Sometimes people don't consider the board space. Well, this NOR Flash that's out there with, I don't know, any pens that are there, 60 pens maybe, address, data, chip select, read, write, whatever it is, takes up quite a bit of space. You can see with the diagram on the right-hand side how much space you need. This is actually taken from the high-tech board, so this is the standard way of implementing NOR and Quad Flash. And you can already see just from a visual perspective how much space savings you're going to get on a board without suffering too much of a performance penalty in application execution or maybe just data storage. So just some notes on the SPIFI. It's not been tested on any other memories besides flash memories. It's really for flash memory interface. It's not supposed to be used for writing stuff in a kind of execute in place or RAM, random access mode. It's really for just sucking stuff out in a execute in place. It's a flash, basically. It's a flash interface. Yeah, that's pretty much what I wanted to make clear there. It is really used for flash. It's really used for taking in data. It's not really used for writing stuff out in a random access mode. You can program it. You can use it to program the SPIFI, the quad flash, but it's really for execution and storage. So the summary, so it's easy to use. You can just use the boot ROM to automatically identify your external quad SPI flash. Most of them are supported. Any new ones, it will revert to the safe mode. You can save board space. Execute in place can be anywhere from 60 to 70% based on CoreMark. That's what we've used for benchmark. If you have your own application, It may be worse, maybe better than that, but this is kind of the guide we're giving to people, 60 to 70%. Of course, we have to say 70. The marketing guy would have got annoyed with me if I'd said 60, but I'm saying 60 to 70%. Can be faster than 16-bit NOR flash. I didn't have the benchmarks for that, but we will have them soon. Signals, number of signals, board space, that complexity is removed. It's a very simple interface. SPIFI, prefer possible NAND NOR replacement, right? We talked about NOR replacement. We didn't talk about NAND replacement. Well, one of the NAND concepts, if you're kind of come from ARM 9 or Linux world, was you boot from NAND, but you couldn't execute in place from it, right? It was a bit of a disadvantage. Some products then came out with a way of doing that, but you have wear leveling and all that headaches to deal with. What they used to do was take the data from NAND in a secondary bootloader and put it into SDRAM. Well, we can do the same thing with NOR, with Quad SPI. You can take cheap, low-cost, small footprint interface, suck all the stuff you want out of it, and put it into SDRAM, point your program counter up there, and you're back into the kind of Linux world as well. So it can be considered as a NAND replacement as well. We don't have NAND interface on our products, so this is one way of getting around that. Another way is that you can just use our parallel interface to do simple bit bang on the NAND interface. It's also possible. I want to talk about the interprocessor communication, and where this comes from is that, well, we've got 2 cores in our chip, and what the hell are we doing, right? Well, just give you a bit of background. We have this old school Symmetric where you have 2 cores doing the job, and the job is split up between them, and they're all running around getting the job done, right? Well, the asymmetric version that we have is more like, well, you've got a guy that can do a lot of powerful work, and this guy that can kind of help out in the background. He's not doing the exact same work as the other guy, but he's making sure that the other guy doesn't get interrupted, right? So that's the concept, right? So we have basically program memory that's shared, and it's up to the individual, up to the programmer to decide how he's going to share it, how is he going to partition the memory. You've got 200 kilobytes of memory. How much am I going to give to the M0? How much am I going to give to the M4? You decide. We don't tell you that you have to do it this way. There's certain ways that it's more efficient than others, but it's up to the person to decide how they split it. So we don't have it hard-coded. We don't have a rigid system. But we do have a thing called IPC, which is interprocessor communication, where we've given people the way of working with this interface. So basically, we have 2 cores, an M4 and M3, makes up our LPC4300, and yeah, you can separate the processing of M4 with real-time control of the M0. So an M0, I hope you're all familiar with what an M0 is. It's a small little thumb 2 type architecture from ARM. We have lots of M0 products ourselves in NXP, and we've also put the M0 core in here as a companion chip to the Cortex-M4. We've put M0 in as a companion chip to the Cortex-M4 and the 4300. This is what it looks like from a bus matrix. So you want about parallelism, contention. In this case, you can sort of see where you've got the I and D bus. The blue line coming out of the Cortex-M4 goes over to this memory. And then the yellow line goes over to another memory. That means them 2 guys can communicate or can execute independently without any contention. There's 2 separate buses that allows that to happen. The execution efficiency of an M0 is less than an M4, even if both are running at the same speed, doing the same stuff. The M0 is a Harvard or von Neumann architecture, so it takes 2 cycles to do something, whereas the M4 has got the Harvard architecture to the instruction and data fetch in parallel. So we have all this memory, and we have all these interconnects, so it means you can do a lot of different things without contention, right? And it's up to the user to decide. It's kind of like an eye diagram, but believe me, there's lots of different ways to talk to each individual block of memory from whatever bus master you might have. So the DMA can be a bus master, the M0 can be a bus master, the M4 can be a bus master, USBs can be a bus master. So you need to decide how you want to partition that up. There's a lot of flexibility in there and lots of different layers of memories that can be communicated to. So the cores need to communicate. If they don't, well, what happens? The guy falls off the table and someone points the finger. And this is how we've done it. So I don't want to rush too, I apologize for going over time. Don't want to rush too fast through it, but this is how it's done. You've got a Cortex-M4 on the left, you've got a Cortex-M0 on the right. And then in the middle, you've got this shared memory. Well, this is just a standard internal memory. You decide which one you want to share, how much you want to share, how much do you need to share, okay? Then you use the send event and the WFE, wait for event, interrupt handling system that's within the Cortex architecture to let them communicate. So what you do essentially is you put something in a buffer, be it tell the M4 to go and process lots of stuff, please, right? That's the message you send. And when you have all the messages sent, you alert the M4 with a send event command. And the M4 could be asleep. It could be waiting for events. It's in sleep mode, waiting. The next thing it gets this NVIC call saying, oh, there's a message. It goes to the message buffer, sees what the message is, does the job. Also, it can work the opposite way. The M4 can control the M0 and tell the M0, listen, get up off your whatever and get doing some stuff for me. I need some data out of USB. Sort it out quickly for me. So it's very simple, right? It's very simple, but it can be complicated. So what we've done is we've created a ROM-based API. And we also have created, outside of the ROM, we've created Kyle projects that talk about queues, message queues, mailboxes, if you prefer mailboxes over message queues, or else there's a free RTOS version as well where it uses a mailbox with free RTOS. So you can have an operating system running using handshaking and using tasks and using the shared memory to communicate back and forth. So that's pretty much what I'm talking about here. We have a set of software that's framework to allow the two devices to talk to each other. You either have mailboxes or not, or queues. And we also have examples with and without the free RTOS. You look at the header file, it tells you exactly what you need to do. How much memory, what memory, where the buffers reside, whether or not the M4 starts up the M0. That's important, right? What happens when this thing starts up? You saw it reset and you saw this code running from this device. When you hit the reset button, the M4 starts executing first. The M4 is the guy that comes up first and starts doing something. But then the M0 could become the master afterwards. What I'm going to kind of describe, it's very simple, but it kind of gets the message across. The M0 sends a message over to UART. The M0 uses a repetitive timer. So in the M0 space, there's a timer interrupt running. It's hidden takes the NVIC in the M0 is servicing them interrupts. It's doing all its little work all in its own little world. It hardly knows there's an M4 there. But it also sets up these mailboxes, and at some point in time, they start sending messages back and forth. And the messages could be whatever you need them to be. In this particular case, it sends a character over, and the M4 sends the characters back that are capitalized. Then the M0 sends a request to do a power of 3 on something. The M4 sends back the results. The M0 sends some text character, and the other guy replies back. And it goes on like that. So it's a kind of a ping-pong example, but them messages and them mailbox requests could be anything. They could be saying, process the FFT that you've received from the buffer. Point this to over here, service the interrupt, whatever it might be. So it's quite simple, but quite complicated. Well, not complicated, but quite useful as well. The framework we've made, the software is there for you to kind of disassemble or build upon. Okay. Dual CoreMark. So this is the last slide. I do have the results here. The 4300 CoreMark score. Well, if you look at the competition, if you go to CoreMark, CoreMark is an industry standard. All our competition are using it. They claim numbers, we claim numbers. We try to be honest, they try to be honest. Sometimes they're dishonest. We're not dishonest. But in this particular case, we might be kind of pushing it a small bit. But I like this because we are 3.24. We're better than the competition because we've got 2 cores. And they both can run independently. They both can do a lot of work in parallel. So therefore, the CoreMark score is the addition of the M4 doing its CoreMark, and the M0 doing its CoreMark, both at the same time, both of them telling each other, I'm finished, you're finished, send the results out to you are. There's the result. The result is the 2.17 plus 1.07, which is 3.24. And that surpasses the competition we have in the market right now, who are claiming some, kind of, I don't know the numbers, but they're in the region of 2, 2.1, 2.3, 2.34. We're at 3.24. Now, I'm not claiming that the M0 is used for processing, but it can be used as processing. It can do work. We've got an M0 LPC 1100 part that does FFTs. We have a demo out there showing it doing an FFT. It is possible. It's not beyond the realms of possibility. So our CoreMark score, it shows you that we have a lot of horsepower in there. 2 cores doing work in parallel obviously it's going to be faster than one core working on its own. And that's pretty much it. Thank you for your time. Thank you.